This video discusses a concept called implicit differentiation, and before we jump into some examples, we need to talk about the difference between a function being defined explicitly and implicitly. So an explicitly defined function is one where you can say, I have one variable completely by itself, and the function is a function of some other variable. So a lot of times we have y by itself, it's a function of x. Okay, so you've got some examples here where the y is always by itself and we can get everything on the other side is just x. However, some functions are difficult to write explicitly, and therefore we have to write them implicitly, which means that it's just a function that is some kind of correlation between two variables x and y. But I can't say, y equals this thing, and that thing is all a function of x, right? It's a bunch of things with x's going on, right? So I can't get my one variable isolated. And so when we look at functions like that, we can still take derivatives of those functions. The process is just a little bit different. So I have a function here that's defined implicitly. It's x squared plus y squared equals 25, and I want to find dy over dx. So remember that from notation, dy over dx just means the derivative. It's the derivative of y with respect to x. So I'm doing the derivative with respect to x. I want to find the derivative, and then I want to find the equation of a tangent line to that circle, which this is a circle, at the point 3, 4. Okay? So to find the derivative, what we're going to do is we are going to take each individual term, and we're going to do the derivative of that term. So the derivative of of x squared is 2x. When you do the derivative of a y term, when we are trying to do derivative with respect to x, the first thing you do is do the derivative as if it were just x, right? So y squared, I would say 2y, right? I would do the exact same rule that I do for y that I do with x's. 2y, but then with the derivative of something that has a y with it, you are going to chain on the derivative of y. Okay? So we don't know what the derivative of y is because we're doing derivative with respect to x. So I know the derivative of x is 1, but I can't say the same is true about the derivative of y. So every time that you do a derivative and the term has a y in it, you do the normal rule as if it were x, but then we're going to chain on, we're going to multiply by dy over dx. And then I can do the derivative of 25, the derivative of a constant is 0. Okay, so technically that's my derivative, but we want to isolate the dy over dx, so I can say the derivative of this function is, and I have just one expression on the right side here. So I'm going to solve for dy dx. So I'm going to subtract 2x, so I would have 2y dy over dx is equal to negative 2x, and then I can divide by 2y, and that would give me that dy over dx is equal to, if I reduce that, I get negative x over y. So what I have here is my derivative, which would say that for this circle, x squared plus y squared equals 25, the slope of the tangent line at any given point, any xy coordinate point around that circle, is going to be given by the equation negative x divided by y. So if I want to use this fact to then find the equation of the tangent line at this point, the first thing I'm going to do is figure out what the slope of the tangent line is at that point, which means I'm going to have negative 3 over 4. So that's my slope. So I have y equals negative 3/4 x plus b. And then if we use our point 3/4, I would say that 4 equals negative 3/4 times 4. Oh, I'm sorry, I did that backwards. 4 equals negative 3/4 times 3 plus b. So 4 would be negative 9/4 plus b. And if I add 9/4, that would be 16/4. So if I add 9/4 to that, I'm going to get 25/4 is equal to b. So the equation of our tangent line would be y equals negative 3/4 x plus 25/4. Okay, so the whole finding the equation of the tangent line part of this is the same as what you did with explicitly defined functions when you tried to find the equation of tangent lines. The difference is when you do implicit differentiation, your derivative is also going to have x's and y's involved. So instead of just plugging in the x to get my slope, I'm going to have to plug in both the x and the y to get our slope of our tangent line. Okay, the next couple of examples, we're just going to work through finding the derivative. So I'm not going to do the equation of the tangent line. I'm just going to work through this and find the derivative. So I want to find y prime or dy dx, okay, however you want to look at it. So derivative each term separately. So x cubed, that's going to be 3x squared, plus y cubed, that would be 3y squared, chain on dy over dx, equals, now when I do the derivative of 6xy, this is a product. It's 6x times y. So I need to do the product rule. Okay, all of that stuff still applies. So when I do the product rule, I do the first 6x times the derivative of the second. Well, the derivative of y is dy over dx, plus the second, which is y, times the derivative of the first. The derivative of 6x is 6. So I've taken the derivative of every term. I use the product rule on the right side. Now my goal is to get dy over dx by itself, right? So dy over dx means the same thing as y prime. I now want to isolate that. So the way that you do that now, if you have more than one dy dx, is you need to get all of that on one side and move everything without a dy dx to the other side. So I'm going to keep this 3y squared dy over dx, and I'm also going to subtract this one over so that I have minus 6x dy over dx. And that's going to equal, on the right side I would have my 6y, but I would also subtract this over to the right side, so minus 3x squared. So I've gotten the stuff with dy dx on one side, the stuff without dy dx on the other. Your next step would be to factor out the dy over dx. So I would have 3y squared minus 6x, and then equals 6y minus 3x squared. And then I can divide by the 3y squared minus 6x on both sides. 3y squared minus 6x. And so dy over dx, or y prime, however you want to think about that, doesn't matter which notation you use, dy over dx, or y prime, is equal to 6y minus 3x squared over 3y squared minus 6x. Okay, and it's the same process every time. It's take the derivative of each term, don't forget about your dy over dx, and then get the dy dx's together, factor it out, divide. Same process every time when you do implicit differentiation. So, last example, we have sine of x plus y. This is actually going to require us to do the chain rule. So the derivative of sine is cosine. We keep the inside the same, and then we chain on the derivative of the inside. The derivative of x is 1. The derivative of y is dy over dx. Equals, on the right side I have a product of y squared and cosine x. So I do the first times the derivative of the second. Well, the derivative of cosine x is negative sine x, so I'm going to put a negative out front and then just say sine x. So negative y squared sine x, plus the second, which would be cosine x, times the derivative of the first, which would be 2y, chain on dy over dx. Okay. So there's a lot of moving parts here that we're going to have to worry about, because I need to now isolate the dy over dx. So it's going to be a little bit of a process at this point. Keep in mind this is like one term here, cosine of x plus y. I can't change that to cosine of x plus cosine of y. It just has to be cosine of x plus y. But I'm taking that thing and multiplying by both of these, so I'm going to actually distribute my cosine of x plus y. So cosine of x plus y times 1 is just cosine of x plus y. But then cosine of x plus y times dy over dx would be plus cosine of x plus y times dy over dx. And then over here we've got negative y squared sine x. And then I'm just going to rearrange this term a little bit here so it looks a little bit better. I'm going to say 2y cosine x times dy over dx. That's just all multiplied together there. So I just rearranged the terms a little bit. At this point, I'm going to move my dy dx's to the left side of the equation. So that's this term and this term need to be on the left side. So that's going to be, and at the same time, just to save some time here, I'm going to also factor out the dy over dx there. So I would have dy over dx times cosine of x plus y minus, because I've got to subtract this over, minus 2y cosine x equals, and then the other two terms are going to be on, so this is still on the right side, negative y squared sine x, but this also has to get subtracted over, so minus the cosine of x plus y. My last step will be to divide all of that stuff over to the other side. So I'm going to go ahead and do that. And my final answer for dy over dx is going to equal negative y squared sine x minus the cosine of x plus y, all divided by cosine of x plus y minus 2y cosine of x. Okay, and once you isolate the dy over dx, your job is done. So that's a pretty challenging example there. What you have to be able to not only realize when realize that you're doing implicit differentiation, know that you have to chain on your dy over dx every time you do a derivative of a y term. But you also have to be able to recognize that there's possibly some chain rules going on, some product rules going on, and you could have a lot of different things happening given your equation that you need to watch out for when you do the derivative.